So this is tutorial 315. Consider a white liquid film on constant thickness H flowing steadily due to gravity down an inclined plane at angle theta as shown in figure 315 as shown here. The atmosphere exerts constant pressure and negligible shear on the free surface. Show that the velocity distribution is given by this equation, and then the volume flow rate per unit width is shown as this one. So we have this kind of situation. So we have an inclined plane here. So we have an theta. So and then the height of water is given as h. So and we need to calculate the velocity distribution. So and then I hope you could practice the Navier-Stokes equation. So for this situation, it's quite simple because we are using Cartesian coordinates. So this is the Navier-Stokes equation for x-axis. So for the left hand side here, so we could get it is equal to 0. I think I already explained the idea of steady flow. For example, du over dt is equal to 0, and then we just assume that there is only x direction, so means that the velocity of v and w is equal to 0, and then here du dx means there are no changes, there is a uniform flow along the x-axis, so the du dx is equal to 0. So and then if you cancel off all these values, you could get this one. So however, for this situation, okay, so we found that we have a gravity acceleration here, but if you want to analyze on the x-axis, so means that you need to take the component of gravity at this side, at this axis. So we will use g sine theta. So and then, okay, we have two times derivation there. We have del square u over del y square, and then we could write like this one. So we integral it once, so we get this answer with a constant there. So and then we use the idea of our boundary condition. So in this situation, we use the idea of shear stress. So we found that the shear stress, the Newton viscosity law actually, so showing that tau is equal mu du dy. So and then at this situation, we found that the idea is we are using du dy is equal to 0 at y is equal to h. So why we take y is equal to h? Because in this situation, so we found that here at y equal to h, we found that there are no more changes of velocity u according to y. Okay, so at bottom here, so we will have a velocity distribution like this one. So means that there are changes of u according to y-axis here. So mean that du dy will give you something. But after this point, because there are no fluids here, so mean that there are no more du dy after this location, after this point. So we write the equation like this one: du dy is equal to 0 at y equal to h. So and then we could get the value of C1 is this one. So and then we substitute into the equation. Okay, and then we derive for the second time. So we have a du dy. So we bring the y to the right hand side. So we integrate again. So we have integration of du. So we get u, and then we get this one, and then once more time. Again, we have constant, so we write as C2. So and then we need to determine the value of C2. So and then we substitute the boundary condition, y is equal to 0 at u equal to 0. So this is because the velocity profile is like this, and we have a no slip condition here. So it is y is equal to 0, and it will create u is equal to 0. And then we get the value of C2 is equal to 0. So and then if we simplify this equation, we could show that the u is equal to this term. So and then to calculate the volume flow rate, so the idea is simple. So this is the common one, Q is equal AV. So this is actually comes from the idea of mass flow rate. Okay, we have a mass flow rate here. So the idea is m dot is equal rho AV. But if we have 2 points here, for example, we have inlet and outlet. Okay, so we will say that m dot 1 is equal to m dot 2. So we will have rho 1 A1 and V1 is equal to rho 2 A2 and V2. So because we are always dealing with the incompressible fluid, so means that there are no changes of density. So means that we use AV equal to AV here. So that's why we always use this one for the volume flow rate. So, and then because we have here, we have the velocity profile. So means that the velocity here is not constant. So we cannot just straight away calculate the value. So we need to calculate it layer by layer. We start with a small portion. So we know that this is small u, mean the velocity flow at this region is u. And then we calculate the cross-section area. So we have Q is equal A times V. So A here is the cross-sectional area. So the cross-sectional area here is dy times width. Okay, because normally in this 2D diagram, we assume that the width is actually 1 unit. If you're not familiar with the idea of 1 unit, so you just imagine that the width is actually 1 meter. So means that it will not appear in the equation. So we calculate the flow rate, means the flow rate at this one, the flow rate at the red shaded area here. So because this is just a small portion of flow rate from the total flow rate that we have here, so we could write dq is equal to u times dy times y. So because this is the one here is the width. Okay, so and then how to get the total flow rate? So means we integrate these two equations. We integrate both sides. So integration of dq will get q here. So this is actually not the mathematical law. So it is not compulsory to change small q into capital Q. It's just showing the amount after the integration. So we have a q here, and then we have u dy, and integration comes with the limit. So the limit is 0 to h here. So and then we substitute the value of u. So and then we will get the flow rate is this one.